Hello, we have with us Scott Walter. He's a robotics expert and one of the leading voices in humanoid robotic space. Thank you, Scott, for joining. How are you doing?
Good, Devang. How are you? Let's see, it's been a couple of months since we met in person. And,
Yes.
But obviously we've been chatting quite a bit over the summer. A little bit of news this summer as far as humanoid bot space.
Yes. Yeah, a lot of news. And when you were here, we got to meet, we got to hang out and check out Optimus Gen2 in person. Yeah, unfortunately, the mic did not work properly, so I did not publish the whole video. But I was hoping today we can check that video out, and maybe you can share some of the insights about Gen 2 and what Gen 3, maybe speculate about what Gen
Sure.
3 Optimus could have in terms of improvements.
So I'm trying to remember, was I technically your second interview? So I think you had interviewed Eric just before that, right?
Yeah, technically it was my second interview.
Yeah, it was the second. And true to form, the mic failed on me because I have all kinds of problems with mics. As we discovered today that for some reason, the driver for this just suddenly decided to go kaput today. And we've been spending the last half hour. So we're going with a standby clip-on mic, crossing our fingers that we don't have the same
Yes.
problem that we had the last time. But when we met last time, it was when I was in the Bay Area, so it was early June, and we decided to take a trip over to Fremont to the showroom there,
Right.
go for a test ride, and like the latest Model Y, and of course I had a Gen 2 bot sitting right
Right.
there in the showroom, not the actual one, but a 3D printed replica, and we had a good chance to go over and take a look at the kinematics, which most people may have already heard me discuss before because it's not something that's new.
Right.
But for anyone that didn't know what was going on, it was a little bit of a refresher. And maybe it gets us an idea of where they're heading with Gen 3, because there hasn't been that much news, has there, out of
No.
Tesla directly this summer.
Right. Yeah, let me share and we can go over the video
Yes,
of you.
yes. Yeah, so there I am doing the normal description of what's happening with the wrist.
Yeah.
And so we have that parallel mechanism there, in which we can sort of see the black linear actuators that are up there that allow it to move around. And the description is that you've got kind of the yawing movement of the hand and the pitching up and down. And the mechanism is designed in such a way that it will pitch really well. You can get like full degrees of freedom there on the pitching when both of them are moving together. But when they're going different, like I'm kind of showing there, is when you get that side-to-side movement, which
Right.
is a little bit restricted because of the way the mechanism is designed. So as we look in there, we will see that we have the ball and socket joints there that are really designed to spin in one direction really well, but not so well off to one side or the other. And that's okay because the human hand doesn't go very far to the side either. We have some restriction there. And usually I refer to that as like, that's your carpal tunnel syndrome. When you have your hand too far to the left or too far to the right, it's not very good. It prefers to actually be straight. But obviously, we are very used to having our hands pitching up and down quite a bit. And now, the one thing that's nice about having a parallel mechanism, of course, is that both of those actuators can be used to provide a lot of strength in one direction when demanded. And that's a really nice thing about them. When you have a serial actuator, unfortunately, your actuators are carrying the masses of all the others, so that if you need to get like a pitching movement, there's only one actuator that can do the pitching movement, and it's carrying not only the payload, but it might be carrying the downstream actuator, which is typically the one that comes side to side in your pitching. And so that's one of the strengths and advantages of having a parallel mechanism. The other thing that's very nice about this is when you are designing an arm, you could be thinking about the hand and you could be thinking about the wrist, and you can think of them as a separate problem. But to do it right, you really want to kind of integrate them in. So you can design an arm that has a connection mechanism for someone else's hand that can just pop in there. And if you're doing that, that means their hand is fully self-contained and has no idea of what the wrist mechanism is going to look like. Everything's going to be there, and you just have to figure out how to provide some services, which would be like a little bit of power to communication there. But if you're really thinking of having a very complicated hand where you're going to be moving a lot of the mechanisms down into the forearm, well, that means you've got to start routing all that stuff through that wrist. And usually a set of serial actuators stacked together is not going to give you the room to be able to route them through the middle. It's going to be going all over the place. And a parallel mechanism like that actually opens up that carpal tunnel, which is, that's why it's called a carpal tunnel, is so things can run through there. And that's typically where all your tendons go through. So that kind of wrist design is very good with the idea of you thinking of not of a hand, but like a whole forearm. And this is something that's going to be very important going forward, is that while there would be companies that are going to be providing maybe bits and pieces of the humanoids, if they are not really holistic in figuring out how everything fits together, then you might have something which is not as good as it could be because it's not attempting to integrate.
Right.
And again, there's some things that I like thinking about when you look at like a shoulder that's up there. Do we consider that a shoulder joint, or do we consider it three separate actuators that kind of come together to form the movement that you want? So the difference between really designing a full joint with everything coming in and figuring out what their part is, as opposed to like, all I do is I just rotate like this, and I don't know what the guy behind me does, and I don't care what the guy down below me does. And to me, that does not seem to be a really good way of integrating an engineering problem. So, and if anyone's out in the showroom, you might be able to take a look at it yourself. Yeah.
Yeah. So for the forearm, it occupies a lot of space. These parallel mechanism actuators, right? With the Gen3, that's gonna be taken up by the actuators for the fingers, right? So how are they going to fit the wrist mechanism in there as well?
Well, we've got kind of a glimpse from the Wii Robot event where we were able to see what that hand mechanism looks like. And we've also seen, I think, just a couple of videos, not as many as we would like to have seen at this point, of the 24 DOF hand. And somehow that 24 DOF hand looks very sleek and very thin compared to the Gen 1. So I was wondering myself, is that if you look at that wrist that's there, and you look at just those two actuators, which is just there for the wrist, there's not a whole lot of room left for putting anything else in there. And when the 22 DOF hand turns out actually has 24 actuators. I know it's a bit strange to sort of think about it that way.
Yeah.
But how are they? And that's not including the wrist mechanism. So if you include the wrist mechanism they're going to be in there, that's going to be adding like another 3. So that whole forearm is having about 27 actuators in there. And how did they do it? It's like, well, they had to make things a lot smaller and also move things around to be able to get that space. So and again, this kind of comes down to saying that, wait a minute, we can't say we designed the wrist and we designed the hand, because in this case, it's tightly integrated together. So the wrist mechanism, they made those linear actuators a bit thinner. They stuck them out on the outside, and I think somewhere I made a post that shows a little bit of it, and there was a video giving an idea of how that mechanism is going to work. And they actually changed it a bit. So this particular mechanism, that whole actuator actually moves. So when it's going, when the rod is extending out, it's not just moving out linearly, but it's also kind of causing the whole actuator to pivot on a point further up on the forearm. And it needs to do that just because for binding reasons. It's forming a triangle, and it's just like a law of trigonometry that you make one side longer, all of your angles are going to change. And so in order for that to work, the whole actuator has to move. And that means that they need space for it to be able to move in there. But then they changed that mechanism a little bit. They said, hey, you know what? What if we add an extra linkage actually on the output? So that they've got the output shaft which is coming out, and then they create 2 linkages on there that allows it to sort of take the distortion that it needs as you're actually articulating the whole arm. And that way, that everything there stayed stationary with respect to the wrist. And they were able to sort of package it a bit better. I want to say cram it in there. I mean, they just really found a better way of being able to package those two wrist joints, it's opened up a lot of space for the actuators. Now, the actuators they're using for the hand, they've scaled them down, because if we remember what the original ones looked like from the AI day 2, where they sort of showed them, they looked like to be pretty big, and they somehow fit. And they were able to get about 6 of them into the palm. But, I mean, again, that was really tight packaging. And if they were using the same ones and trying to put them down there, they're not going to fit. So they've come up with a different kind, seems like a much smaller kind of linear actuator. And the difference is on the first hand, they had a drive unit and then kind of a bevel gear that made a right-hand turn. And on there, that was the output shaft that resulted in a spool that you would take the tendon on your finger and wrap it up on the spool. And that's kind of how it worked. And the problem with wrapping up tendons on spools, especially if you're using something metallic, there's a lot of bending going on there. And you've got to have a pretty big radius to be able to wrap it around there. If you try making the radius too small, then it bends too much and you'll actually break the tendon. And any kind of metal, I mean, you just think about it, there's work that has to be done to kind of flex it constantly. A lot easier with something like, very flexible kind of fiber, but if you're using something stiff like that, it's a bit difficult. So depending on the kind of tendon material you have, rather than wrapping it around on a spool, if you can just pull on it up and down with a true linear actuator, then that would save you a lot of issues and also make things way more packaged, because you don't have to worry about this weird gearing and it's coming out at 90 degrees and things spinning and everything else. So it looks like they came up with some sort of sleek design to allow them to cram 24 of those in there in rings. So basically, 8 here, 8 here, and another 8. It makes it all the way on down there. And remember the tennis ball catch?
Yeah.
When they were catching the tennis ball, I was looking at that hand. I'm like, that looks smaller than the original one, and then got more degrees of freedom. So a pretty good packaging job. But I think it still has challenges despite that. Otherwise, we would be seeing that hand in action more, because right now everything that we're still seeing is just the Gen2 bot. It's the Gen2 bot that's now at the diner in Los Angeles.
Right. We haven't seen Gen 3 hand doing anything other than catching the ball.
Yes, exactly.
And the gestures.
Exactly. So, right. And we saw the proto assembly line where it looked like the Optimus. I would call it like the 2.5 or the Gen 2 refresh, which is pretty much the entire same body, but the forearm is different. We saw an image of that in the quarterly report, the Q1 report. So we thought, that's what it's going to look like. But we know since then there's been a lot of changes. So this summer, there's been no direct news coming out of Tesla, save a few things. The Tesla diner opening up. We got a chance to see the teleoperated Optimus being used for the popcorn dispenser, and a little bit of news at the X takeover. But most of the news we've been getting have been other press articles about the status of the Optimus program, where Tesla was reached out and gave no comment. So the first one, I think, was in late June, saying that, all right, the Optimus production is basically come to a halt. So that was a big change from the expectation of several thousand in the factories this year to now the Gen 2 is not, and all the focus is going on Gen 3. And I think that was kind of confirmed at the X takeover, where both Elon and Lars spoke to that, and the fact that, what was Elon's quote? Something that almost nothing remains, or something like that.
Almost nothing remains the same in Gen 3 compared to Gen 2.
In Gen 3. Okay, so what do you think that means? Because it literally means, head to toe, there's going to be a change.
Right.
And that might mean a lot of the actuation strategy that they're using is going to change almost everywhere. So if nothing remains the same, it could be radically different. And as you know, I've spoken about this a lot, about different kinds of actuators. You got rotary actuators and you got linear actuators, and there's pros and cons of both. And we have some humanoid bots which have really gone into this full linear actuators, but there's only 1 or 2 that have done that. Really just one that's really deep into it. Others that are kind of well, we like it for some actuation strategies, And then there's many others which are just pure rotational. And Tesla is in the middle. So I think there's like 14 linear actuators and maybe 16 rotary actuators in there. So it's the rough balance in there. The big question is, what's the strategy going to be going forward? What do you think? Is it going to be all rotary, or you think it's still going to be a mix?
They're going to focus on the design, but I don't think they will focus on too much of like cost on Gen 3. Right? So whatever makes sense in terms of actuation. But you talked about there are a lot of improvements that can come in design of the hips and,
Yes.
and having an extra foot degree of freedom for the foot, maybe rolling. Shoulders can have improvements, right? So we will see a little bit of everything, like everywhere. But I'm not sure if they will just go for rotary just because supply chain is not there right now. They will try to optimize for the best design and then figure out the supply chain later. Is what my feeling is.
I agree that the one of the things was like some issues with the supply chain for the linear drives, which would have to ramp up. But that's a very important signal that they kind of have to let everyone know right now. There are so many companies that are sitting on the sidelines trying to figure out, do we help in this supply chain? And so the supply chain for linear and for rotary are going to require two very different things. The rotary seems to be the consensus is a harmonic drive for your reducer. There's other possibilities that could be coming along, maybe cycloidal, but that seems to be that the supply chain is sort of focusing there and is also trying to ramp up. And then if you go to the linears, well, you gotta have a couple other things, and one of them is the planetary roller screw, which is a very different beast, requiring a very different kinds of equipment to be able to produce this stuff. And the thing about it is that if you tell a company that, we want you to produce a large volume of this particular part, and say, okay, great, we'll go out and we'll find the equipment that's actually able to produce that. And depending upon the kind of gears that they're producing, it might be some very standard kind of stuff that they can get from a variety of different suppliers. There'll still be a little bit of lead time, but you can get them in there. But then there may be some other things that are kind of exotic and really rare. And it's, remember, most of these people who are supplying it aren't building the CNC machines. They're buying them from someone else. And those CNC machines are usually designed to do certain kinds of tasks. In some cases, you're asking them to do something they can't do. So that means those companies have to then go and say, we're going to have to completely redesign this piece of equipment. And by the way, because we sell these in very low quantities, it's not like we get them sitting on the shelf that you could just buy them. So there could be a long lead time, 6 months, 9 months, 12 months, or something like that, even longer, especially if the designs don't exist yet. So as you go down those different tiers, you've got to start letting them know that this is the direction you're going in. And right now, Tesla is kind of leaving us guessing. It's like, okay, if I was someone thinking of supplying components for linear actuators right now, and if I think Tesla's going to go that way, then I think, okay, I've got probably a pretty good market to go in there. But if they suddenly say, nope, we're not going to go that way, then I'm looking around, okay, who do I sell this equipment to? Oh gosh, nobody needs it. So that could really impact the supply chain. I'm assuming back channels, they're talking to everyone in the supply chain to let them know what they're going to do. So even the same thing with harmonic drives, if they suddenly pivot on that, well, now the demand for rotary actuators coming from Tesla is going to double if they decide to go that way from what it was before. And now you're going to have the same issue with like, what about the harmonic drives and being able to mass produce those things. And there's also, right now it is taking a while to produce harmonic drives. There are, potential technologies that could come online based on another signal to the market that, yes, we need to be able to produce these kinds of harmonic drives at volume, and we need to be able to produce them quickly.
Right. There was story by Late Post Auto. They had some insider news from Tesla suppliers in China. And the thing that was most striking to me was the part about the dexterous hands. So Tesla is still testing samples from multiple dexterous hand suppliers, trying at least 3 different technical approaches. So if that is true, I mean, they are not completely committed to the tendon-driven hand, and maybe still working on the design, or not finalized what they want to commit the full production on.
Yes, and I think that's part of what we're looking at is the actuation strategy, again, for those tendons is kind of tricky, and each of those drives is pretty small, so they can only produce so much, in this case, force, because I assume that, they're not really rotating, so they've got to pull on that. And if the force is very small, that means overall the hand will be very weak. Its grip strength will be kind of poor, and you've got other things that you've got to control in your actuation. So they've got so many degrees of freedom in the fingers that it's not just the clenching force you have, you also have the kind of the spreading of them. And
Right.
a lot of times the spreading of them needs to resist a force. So if I'm pinching, for example, when I'm doing that, I'm applying a lot of force down here on my base knuckle. And part of that will be like back and forth. And if there's too much force in there, it can cause it to slip. So that's one of the harder ones to control with there could be little motors, which are the same strength as the ones that are closing it down here. The problem is the moment arm they have is so small, it's such a tiny lever arm there, it's really hard for them to apply the force that you need. And so they could be taking a very different actuation strategy. I don't know if I'm going to predict this, but it wouldn't surprise me if they decide to go with a hybrid approach.
Okay.
And the reason why I think they might go with a hybrid approach is that I've seen a couple out there. And most recently, there was a company from Korea last week that kind of showed off a new robot, especially their hand. And I've been looking closely at it, and I'm pretty sure that they use tendon strategy for flexion and extension, but it looks like they're using a mechanical linkage for being able to do the ab and adduction. And I think that's a good strategy for many reasons. One is it allows them to really deliver the kind of force and positioning accuracy that they need to hold that in place, but at the same time being able to very efficiently come up with the grip strength that you need to have. So I would not surprise me if Tesla decides to do something like that as well, and say, and this is kind of the way I see the problem, is that when you're looking at abduction, it's really just one joint you're trying to move. That's it. When you're doing flexion extension, you're trying to move 3 joints at the same time.
Yes.
Yes, exactly. So we can see this hand here. I think it's like, is it Robotics, or I think might be the name.
Yeah, Robotics from South Korea.
Yes, and they seem to have pretty good precision there. And in some images, we'll be able to see that it clearly looks like there's tendons running through the fingers. And I would say that they probably are using tendons because this comes from out of a research group that I think it did the Ambidex robot a few years back. And that was like an all tendon driven. I mean, right from the torso, you had tendons coming all the way through, controlling your arms fully. And so they know a thing or two about tendons, no doubt about that. But they probably also realized that the strategy of being able to control the abduction was a bit tricky. And if you look at their hand in a few, you'll see a glimpse of something. It's like, oh, that looks like a mechanism going up there. So it's not like they're telling me that's that, but if you look at the images just right, you might be able to notice it. So my feeling is that if you're trying to move more than one joint, then it makes sense to use a tendon. So you have a tendon come down here and it allows you to be able to do that. But abduction is a single joint problem. And because it's a single joint problem, you might think, hey, maybe we just go ahead and use a direct mechanism or linkage in there to be able to control that. The other problem that always crops up, especially with tendons, is that you can only put them in tension. Compression is useless with a tendon. So if you need to move in the opposite direction, that means you need a second tendon over there, which means you need a second actuator, or you need to use some sort of capsid mechanism that you wrap them around counterclockwise, and that gets tricky because you've got to try to get the tensions of both of them right. And we could see from the original design here that what Tesla had, when we look at things like abduction and everything else, they're running a lot of tendons through here to be able to control all these. And I think that's when I finally figured out where their 22 DOFs came from. And the irony is that when you go through here and count out how many actuators they would need, you actually get 24 actuators, which you think, wait a minute, if there's, and again, let's be careful about what we mean by a degree of freedom. Technically, a degree of freedom is something that you're able to control. Usually, it actually means the number of actuators that you have. So we should really call this 22 joints. So that's how many joints are up here. They're able to move in different directions. And in order to get that control, because again, sometimes you need two actuators just to do ab and adduction. And then you got to do that, 4 times here for the fingers, and then over there, that starts to add up. And you do it, and you end up finding out, hey, I need 24 actuators to be able to control these 22 joints.
Yeah. Yeah, another thing was Elon's not been talking about tendon-driven hands since, I would say, the 10/10 event, October 10th. And so
he's mentioned a few times that how great the hand is. I think at some of the earnings calls.
Okay.
But you're right. Recently, there hasn't really been a whole lot of discussion of that hand, and it may be that it just became more challenging not only to control, but teach. I mean, that's the other thing you got to remember is that you can have a hand that's really dexterous, but then it could also become very tricky on how do you teach the hand to grasp things if you've got so many degrees of control. Are you doing it with a data glove of some sort? Or are you just going to be doing it with cameras that are looking at the hand and trying to figure out what that movement is? And so that also could be something that's problematic.
Then there was this Lars's statement about some of the Optimus team members going to a hand surgeon to educate themselves about how the hands work. So they do want to keep pursuing, it seems, this tendon-driven approach and stay as close as possible to the human degrees of freedom.
Yeah, it could be that they are. I don't know if I should take a victory lap here because I was the first one to suggest they should visit a hand surgeon back in the fall. And that was after one of the podcast appearances with Gustav Andersson, who is a hand surgeon from Sweden, along with Roy D'Souza on his podcast, where we talked about that hand right after we saw it in the We Robot event to understand and he explained pretty well to us how the hand works, the importance of all the tendons. And I learned so much from that. I said, you know what? If they haven't consulted a hand surgeon already, I think they should. And so I'm glad to see that they recently decided to go ahead and do that, because there will be all kinds of benefits, even if you're not thinking of doing the tendon-based, to understand how we make those movements. So there's a certain amount of biomimicry, but there's also understanding that the hand surgeons have a very good understanding of what are the grasp and positions and everything else, how they test the usability of the hand, what kind of dexterity they have. And they also have to make a type of engineering decision. Whenever we build something, we have to decide, okay, do we want perfection or do you want kind of good enough? What's the minimum viable product you have to go through? And that's kind of a part of good engineering decisions. You just got to decide that this is important, that's not so important, this is feasible, that's not feasible, and go ahead and do it. Surgeons have to do that all the time. So, the ideal outcome is that you have an injury and they're able to restore you 100%. But the reality is like they can't, because there's a lot of damage and there's some compromises and there's some decisions they have to make, definite trade-offs. And they have to do that consulting with the patient to say that, we can provide you this kind of capability back in your hand, but you're going to lose this.
Yeah.
Tell us, what's going to be important for you. And a lot of it is looking at like a person's profession. It may be they're losing some kind of capability in their hand. So, one example that talks about is a joint called like a sloppy CMG joint. So You could have some sort of injury that your thumb just is moving around and you can't hold anything because you just lost strength there. Well, there is a surgery that you can do down there that you can fuse that so your thumb stays in a very stiff position. Now you can grasp things to do something. Well, if you're a carpenter or something like that, that could be very useful. That could be something that you absolutely need because it's going to give you the grip strength. But if you're not, it may be that that's not actually the kind of surgery you want. So that's why part of the reason I encourage them to talk to a hand surgeon is because they're concerned with outcomes and what you need and don't need for those kind of outcomes. And so they could probably also help them align themselves like, oh, this is very important. What is the importance of being able to have these kind of different grasps in movements of our fingers? Do we really need them? So to make sure you don't have overkill and at the same time make sure that you're not coming up short.
Right. Okay. Yeah, and the change of plans that Elon mentioned in Q2, that was in very short order. So Q1, he was like, we are going to produce thousands of Optimus. We were not sure whether he's talking about thousands of Gen 2 or Gen 3, but the picture showed generation 2 dot something, right?
Mm-hmm.
And in the next earnings call, which was the recent one, he says instead of making hundreds of thousands of Gen 2, we should just commit to Gen 3 and make hundreds of Gen 2 and switch production to Gen 3 next year
Yes.
to scale up.
Yes.
So kind of confirms that they were planning to scale up thousands of Gen 2 robots, and maybe because of the design overhaul, they don't want to commit too much to the supply chain and the manufacturing side for Gen 2.
Yeah,
Is that...
yeah. I think that that was the hope. Going even back in January, I think that's when they first mentioned that the potential of ramping up to 10,000. I forget that the earning call was much later, so that was like more in April. So even in April, their sights were still on that, and then within a matter of weeks, suddenly it's like the decision, like, wait a minute, we're not seeing the progress that we would want to have. And I've said this many times, people keep on wanting to know, when do you scale to 1 million robots? And it's like, that's not a big deal. If you wanted to tomorrow, you could take a design and figure out how to get it, but you don't scale a crappy robot. And so that's not, they clearly looked at it and said, we don't need 1 million of these. That they're not able to perform what we want. What is the bot that makes sense to scale? Again, supply chain effort and stuff like that. The last thing you want to do is a rug pull on your supply chain that is like, oh yeah, we're going to ramp up on this one, and suddenly say, you know what, we completely changed the design. The design is so different that all those things that we told you to start scaling on, you don't need to do that anymore. So hopefully they're able to come up with a design that iterations of that going forward are just going to be iterations in the supply chain and not a major overhaul. So again, that decision of linear versus rotary, that's a big decision because the equipment that's needed to make those different components is so different. It's going to mess everything up. But if you're just talking about making your things lighter and tighter, improving tolerances and doing stuff like that, well, that's something the supply chains are used to doing over a matter of time anyway. So that will be all right. So it does make sense. It does kind of put the program behind a little bit. Disappointing that we're not seeing it in the factories already. The expectation was that, by the end of the summer, we would have seen a lot of that. So we haven't, unfortunately. And then the next thing, of course, is the data collection. It's a bit interesting what that's going to look like.
Yeah, there was a Business Insider story on Tuesday. Mm-hmm. And it says Tesla's moving away from motion capture suits and VR headsets for teleoperated data collection and focus more on human videos and train the robots model directly from human videos. And it's not a surprising thing considering they showed a demo of, I think in May, a demonstration of autonomous capabilities using first-person human videos. So which is just bare hands. So first-person videos of people doing something with their bare hands and collecting data for Optimus. So that's been going on for a while. What do you think? Is it kind of really a quick shift, or is it kind of they are seeing something internally which led them to do this?
Yeah. Well, when I read the article, at first I was wondering, what the sources were, because it's always like according to sources. And they mentioned a few things, and it's like, oh, wait a minute. I think we've seen this already. So this data collection here, that goes back to, I think, May of 2023 in one of the Optimus update videos, where we're seeing a configuration exactly like they describe in there. A helmet with 5 cameras on there and a big heavy backpack, and the operator actually picking up real things. So the difference is that the current teleoperation, the human is not actually manipulating anything. They're not manipulating parts or anything like that. It's the robot that's doing it, and the human is just looking through the headset and trying to move their hands enough to go ahead and do it. And that's kind of frustrating. I mean, imagine what it would be like trying to fold a t-shirt without you even being able to feel what it's like. You're trying to tell someone else how to move their hands around, which is basically what the teleoperation is. Whereas we already saw over 2 years ago that they're doing it this way, and that the operator is actually manipulating real-world objects.
Right.
And then you're taking the movement of that operator and then putting it into the simulation to train the robot from there. So we've seen Tesla's already done that. And I think it's not so much why are they like moving away from the mocap suits. My big question is like, why didn't they continue doing that in the first place? Why did they move away from that and deciding that they're ready to revisit it? And it may have been that there were some issues. It was just kind of too hard to get it to work at that point.
Right.
And they said, oh, okay, we'll go to the mocap suits. And remember, with full self-driving, there's always been this big discussion about LiDAR, right?
Right.
And it may just turn out that using teleoperation and motion capture, stuff like that, is going to become kind of like the LiDAR of teaching robots, and that maybe the real way of doing it is with the cameras. Now, there was a pretty informative post by someone out there that was really analyzing it. It's like, what does this really mean? And it's not going to be that they're just throwing cameras on everyone that's on the production line or doing something like that, because you'll get way too much diversity of data.
Yeah.
What they want to do is they're first going to really train the operators on the proper procedure to do a particular task. This is how it's done. Now let's go ahead and do it many, many, many times from different angles, capture all that. And there's going to be like obviously a little bit of variation, because sometimes when you do a task, for some reason there's a snag or something doesn't work out right. But the thing is, you don't want to have people coming in and doing a task they're not familiar with and doing it in an order or doing it in a way that is just not professional, I guess you could say. So you want to make sure everyone's trained. So again, think about t-shirts. How many people actually know how to fold a t-shirt properly? Everyone has their own way. I mean, there's so many different ways of doing it. So just imagine every teleoperator you have to come in and say, okay, show Optimus how to fold a t-shirt. And they just do it their way. I would think it will get so confused to not know, well, what's the proper way to fold a t-shirt. And the best thing is to say that this is the procedure, this is how we go ahead and do it. And that's what happens on the factory floor anyways, is that there are a lot of operations that are going on, and everyone is told this is the best way to do it. And if you come up with something better, great. And then we want to make sure everyone else does that as well. But you want to make sure everyone is training it for consistency, because that's how you make sure that you have the quality and also the quantity that you need to produce, because you're finding a way that it is going to be the quickest and easiest.
Right. Yeah, so when they showed the autonomous demo learned from first-person videos, there was this frame in that video which showed people, humans actually performing the tasks with the bare hands. So they were able to take that and transfer all those movement to the kinematics of robots somehow. So they have like a labeled data for training the robot. So the Business Insider story is not very surprising, considering Milan laid out the plan pretty clearly in May, saying like
Exactly.
that's the plan, that they are going from first person video to third person videos, and then using reinforcement learning to refine it more.
Yeah, and they may, and in some ways they might be going back to first person videos because we've seen they were already able to demonstrate that. Now,
Right.
what they demonstrated was they were using the first person video to have the robot mimic the same movements on in the simulation. And I'm not sure if they then showed that they could capture that and actually have the real Optimus do that. I know there was some autonomy that they showed of picking up blocks and moving those things around. And I'm assuming it was kind of trained that way. So in that particular video, we did not see the next step. Oh, okay, we've gone from real to sim, but
Right.
were we able to go from the sim to real? I'm assuming they did, but again, it may have been at that time the progress they were getting was not moving along the way they wanted, so they took this other approach, which may just turn out to be a crutch. It's like, oh, okay, you can get some capabilities out of that, and you know, the one reason I would have moved towards that was not so much training the bot, but we've built this hardware and we're not quite sure what it's capable of doing.
Mm-hmm.
And we want to put it through its paces. And we're having a hard time with this reinforcement learning or imitation learning or whatever it is. We just can't seem to really get it to go, let's just teleoperate this thing and let's see what it can do. You know, does it have the dexterity to fold a t-shirt? So, because I was wondering, like, wait a minute, what are they doing folding t-shirts? You know, I didn't know Tesla was in the t-shirt business. And again, it probably was more like, well, no, we're just testing capabilities. We want to see what it can grasp, what it can't grasp, how it can manipulate fabrics and everything else to make sure that the hardware is good while we try to figure out the software business off on the other side. And so it could be that they're taking many, many different approaches. And if you think about even the way FSD has gone, Tesla took a lot of approaches, many, many different ways. And probably because they weren't sure that this end-to-end business was going to work. There was a lot of people who were probably like, oh, no. And they went and did it. And then they're like, my goodness, this is easier than we thought it was going to be. And the performance is a lot better. So you remember when they made that shift to version 12, it was just like, wow, it turned out that was the solution. And this is the same thing that's happening in robotics, is that once everyone figures it out, and they're going to look back and go, oh, the answer was obvious.
Right.
But getting that obvious answer, it's going to take a lot of stumbles and, you know, going down different cul-de-sacs and maybe doing some things that didn't look, you know, really the promise, you know, in retrospect, you'd say, oh, that was not a promising way to approach the problem. But, you know, it's easy to Monday morning quarterback everything. So,
Right.
yeah.
Yeah, so you go on to talk about the legs and the feet mechanisms here. Overall, with Gen 2, what are the, like, you would say, like, top 2 or 3 things you would like to see in Gen 3 improve in terms of actuation?
In Gen 3, I'm assuming they're going to completely change the hip design. I really think they're going to go to rotary all through.
Oh.
That's my guess. That's what they would probably do. And it's mainly it's the actuation strategy that I've referred to as like the R strategy, where the highest actuator up on the chain is able to do abduction, and then they have rotation, and the very last thing is flexion. And
Okay.
everyone else took the same approach on their first generations. So if I made a post back in the spring where I kind of had a histogram showing everyone's first generation designs for the hip, and they all pretty much had the same kind of order of operations as they did for Optimus. But on the second generations, they moved away from what I call the ARF design to the FAR, where they do flexion first, then abduction and rotation. And the reason of doing the flexion kind of down the chain is this whole problem with the serial link mechanism is that you're having to carry the mass of all the actuators downstream. And the flexion is the most important thing to moving the legs or walking. And if you have flexion up really high, it's like, it has to carry the mass of the other actuators. So everyone was trying to avoid that. But it turns out whatever the advantages of that were, it sort of was not kinematically favorable to do that. So they all have shifted to FAR, and it's like, whew, everyone's gone over there. And there's also now been variations on how the FAR design is, of people putting in some interesting little angles and everything else. So my suspicion is they'll be able to do something like that. Now, I suspect they're going to keep the same thing. I mean, the reason why I was leaning that way is that one of the things that they did in their torso design, and this has also been copied by several other companies, the same idea is that you don't need to have 3 degrees of freedom built into your torso. So in other words, like my whole torso could lean forward, could lean side to side, and also twist. The reality is you only need the twist and you only need to kind of lean the side to side, because the bending forward can happen at the waist as well. So through your hip joint. So there's a certain amount of redundancy that can be used there that means you don't have to waste an actuator there. So, waste not, want not, I think it's a joke I'd made something about that. It's like, don't waste an actuator in your waist. That's really not needed. Now, in an ideal world, yeah, it would be nice to have, because we humans can kind of do that because we have this very flexible spine. But day to day, you'll notice that most people keep their torso almost flat and rigid. And that when we go to pick up something, a lot of times we are really leaning forward through our hips as opposed to doing it through special actuation there. So that reduces your mass, that reduces an actuator and everything else. So they'll keep something like that. But I have a feeling that they're going to completely change the hip design, which means those linear actuators are going to go away, more than likely. And now I think they may keep them in a couple places. So everyone's sort of ankle and let's say wrist strategies, a lot of people are trying to do a similar thing of having that parallel actuation on the wrist that you would also want to do down on the ankle. Because you want a very slender kind of ankle joint there. Again, you have the advantage of the parallel actuation, so you can have double the pop in kind of going up on your toes as opposed to having a single actuator there. And it's a very common strategy everyone else uses, except you don't have to necessarily use a linear actuator there. You can also have a rotary actuator that has a linkage that goes down there, which is what Unitary and everyone else does. So when you look behind them, you can see it. The thing is, that linear actuator package is so much better in there because, that's the way your calf bone is kind of set up. It's long and skinny, right? And if you're trying to put a rotary actuator in there, it kind of fits in there a little bit funny. And so if they decide to keep some linear actuators, I would think it's going to be down in the ankle, and it will probably be in the wrist. Whether they need it in the elbow, because that's the other place that they have in the elbow, I'm not sure. So if they were going to keep it, yeah, maybe, but I would not be surprised if they decide to drop it there. And then, but I have a feeling the upper part, they'll probably get rid of all the linear actuators there.
Is there a chance?
Which would make sense if nothing remains, right? That was, I think, the quote.
yeah, that's what I was going to say. Like, if nothing remains same, is there a chance they are do something radically different, like compliant drives that 1X uses?
You never know. They maybe they come up with something different there that using tendon drives. So depends upon how well the tendons have been going in the hands. If they're finding it's really hard to get the tendons to work in the hand, they'll probably say, I'm not sure I'd want to do that to the rest of the body. But if it's going well, then it would be possible they would want to do something like that. I don't think so. I think they would still go direct. And they're probably going to want to do something to make sure that those actuators aren't popping out like that. Just packaging them a little bit differently, which is probably why I think the FAR design is also better that way. The way you package it is that you can almost hide all the actuators. They don't stick out kind of like they do there. The other disadvantage that it had with Optimus is that the flexure is down really low. So it's actually unnaturally low. It's about, maybe 6 inches or more lower than it is in our bodies. And that cuts its stride length. So it doesn't have as big a stride. And that's one of those things that can come in and kind of compromise the overall speed and being able to walk around. So that would be another advantage to going to the FAR design, is that flexion actuator comes up a little bit higher, which means you're able to get a bigger stride.
Where are you at in number of Optimus robots that we are going to see next year? 2026.
Oh, next year. Okay.
Yeah.
I think
this year we know it's going to be hundreds or maybe less.
Yeah. This year, the hope is that by the end of the year they already have a couple prototype Gen 3s out there. So I would think they would have a couple. I think Elon is hoping that they would have 100. I'm not sure that they're going to be able to hit 100 of that, because my feeling is that it's still so early in their design process. It's going to be tough to be able to do that. Assuming that they have that, then the year after, so in 2026, you might be able to see your first 1,000 of that. Because I have a feeling their supply chain, everything is going to be very, very, very different. And then you can start seeing potential, and so that's assuming, let's go to December and say they come out with the first couple that they're, and it's just absolutely great. I mean, you can look at it, it does everything that you want, and then they're going to kind of start this ramp up, which means that the following year, 2026, you're looking at 1,000, maybe 2,000, something like that you'll be able to get to. But it's looking so good that you're telling everyone in the supply chain, ramp it up, because in 27 we really want to start going. That means 27 you're able to get to probably scale it up by a factor of 10. So you're able to get up to that 10,000 in 27.
Right.
And then from there you can probably make it up to the ladder. So I think in the last earnings call, Elon was more like, 1 million by 2030 for sure. So it seems to me that's it. So you reverse engineer it, okay, and assuming you can kind of get that 10x scaling every year, then that's possible. So 28, you're at like 100,000. 29, you're at 1 million. So then it becomes kind of easy. So if you're 10,000 in 27, 128, and then you could hit 1 million in 29. Already there, and that means you don't have to be quite 10x. So maybe you're a little bit shy of that to be able to hit that mark. Now, getting up to 1 million while challenging is fairly easy. So I think a lot of the humanoid bot companies would be able to scale up to 1 million. Once you start going in the tens of millions, then the challenges really start to come in there. Then it starts like, okay, now we're starting to really test everything, and doing factors of 10 from there become harder and harder. So, yeah, I could see going from 1,000 to 10,000, 100,000 to 1 million. Boom, boom, boom. That's pretty easy.
Right.
But now, now we want to go to 10 million. Now we want to go to 100 million. Mm-hmm. and then we want to get up to 1 billion. So, there the scaling would slow down. But there could be these other effects that are going on there that we don't understand that allows the curve to go a little bit faster. So the first million, probably by 2030, is possible. But unfortunately, the next 2 years will probably be disappointed with the number that we see coming out, and then what we see in the factory. I mean, I hope we start seeing actual useful work being done in the factories, next year with a Gen3 bot.
Right. And here's a picture.
Yes, there it is.
So everyone knows I was also there.
Yes, exactly.
Yes.
Yep. And yes, and at the end of that last video, someone actually recognized me coming into the showroom there and had a couple of questions. Right. So we told him, he would make it in the video. He's probably wondering, it's like, where is that video? 2 months later.
Yeah. Thank you so much, Scott, for your time.
Yeah.
It was wonderful.
You're welcome. It's nice to have these chats and kind of catch up and where we are. And again, I want to thank you, because I think I did somewhere in the interview is to say a big thank you to you and the service you're providing the community to keeping us up to date with everything in the humanoid space. So a lot of times, the first time I learn about some new development in the humanoid space is from you. I'll post an X, and I'm always like, where does he get this information? I mean, and I asked you, and basically it comes down to hard work. I mean, you're going out there and really digging and finding a lot of these things. So it's not like it just falls in your lap. You're going out there and doing it, so we don't have to. And I definitely appreciate what you've been doing.
Thank you for the kind words. And I'll put the link to your Twitter account in the description, and also the Roydens podcast episode that you mentioned in the description. Mm-hmm. Thank you so much, Scott.
Yeah, you're welcome.
Yeah.